Hi, this is going to be the prep video for test number 6 for 3004. We're going to look at the 2017 test 6, and this is the first one on heat transfer. So, first question, a GPU consuming 200 watts dissipates this heat on one side of the chip only. This side has an area of 5 square centimeters and is connected to a water cooling system. The cooling system is a copper plate, which is 1 millimeter thick, followed by forced water convection cooling with a coefficient of 5,000 watts per meter squared Kelvin. The free stream temperature of the water is kept at 23 degrees C. Estimate the surface temperature of the chip if in situation A, there's a 50 micron layer of thermal paste connecting the chip to the copper surface of the heatsink. And then B, instead of the thermal paste, we've got the heatsink connected directly to the GPU with a thermal contact resistance of this. And then explain why we don't need to account for two thermal contact resistances in part A when we used the thermal paste. So what we've got is a situation where we're going from a chip that's dissipating this much power at a constant rate, but depending on how effectively we can move that heat away, the surface temperature of the chip is going to end up at an equilibrium of a different temperature. So if we can move that heat away very quickly, then we would have a surface temperature that's not well, actually, ultimately we're moving the heat away at the same speed because we're dissipating 200 watts. But the question is how hot the temperature of the surface needs to be to get that speed of heat moving away. So if we've got really effective heat transfer, sort of really efficient heat transfer from low resistances and really effective convection, then we would need a low temperature gradient in order to drive that. So kind of like low resistance means you don't need as much of a temperature difference to get the same heat flow. So for the information from this, we're going to go over to the test recap, where we've got information about adding thermal resistances and how to deal with this. So the way to discuss this is to use the kind of electrical analog, where we've got that every element has an effective thermal resistance that is defined as the temperature difference across it divided by the rate of heat flow through it. So if we have a number of elements in series, then we can say that the total combined resistance of that would be the sum of the resistances of each individual part of it. So we can say something like the total resistance would be equal to, depending on the situation, we've got the resistance of, so the first one we've got the resistance of the paste. And let's see, do they tell us anything about the copper plate? Oh yeah, so cooling system is a 1 millimeter copper plate followed by forced water. So we've got first the paste, and then we've got conduction through the copper, and then we've got the convection, resistance of convection. Okay, so this is going to be the first setup. So resistance of the thermal paste, then resistance through the copper, and then resistance of the for the convection surface. Then what we're going to do with that is say that the total resistance is equal to the total temperature gradient divided by the rate of heat flow. Now the temperature difference is going to be the temperature of the chip, so the surface temperature of that GPU, minus the temperature of the water. So maybe we'll call that T infinity. That's our free stream temperature. And then we're dividing that by Q dot, which is our 200 watts. So yeah. .23 degrees C. Okay, so if we are able to figure out the total resistance, then we can get the GPU temperature by taking 200 watts times this total resistance plus 23 degrees C. All right, so then the name of the game is to figure out what this total resistance is. So then what we're going to need to do is write down what these resistances are for the different elements. We've got a conduction part, another conduction part, and then a convection part. To figure out where what these resistances are, we can use the heat transfer laws that are associated with them. So we'll need the conduction and convection one, for instance. So from this bit of information, you could see that the rate of heat transfer is equal to Ka times delta T, where the negative sign is absorbed into that, divided by the length across this thing. So that means that if we needed this to be relating the resistance to the temperature gradient, then in other words, this is supposed to be the conduction resistance times the change in temperature. Wait, that's not right. It's supposed to be 1 over the conduction resistance times the change in temperature for this equation to work out. Now, this refers to the change in temperature over the conduction part, over just from one side of it to the other. Then this tells you that a conduction resistance, so a thermal conduction resistance, is equal to L over Ka. All right, and this is actually the same as the as electrical resistance, right? So if you were to have if you have some element, then the resistance across it is the length times the resistivity, 1 over the conductivity here, divided by the area. Okay, so that's our conduction resistance term. And for the convection resistance term, you could use the same sort of a logic for this expression. So R dot for Q dot for convection is equal to HA of the surface times delta T. And if this is supposed to be 1 over R delta T, then it tells you that R for convection is equal to 1 over HA. Okay. So this is really just some background information on how the resistances are related to those heat transfer pieces of information, those heat transfer equations. So now that we've got that, we can jump right back to the particular problem that we're trying to solve here. We've got our background information. So the total resistance here would be the resistance of the paste plus the resistance through the copper plus the convection resistance. And now we can jump over to a calculator. So we'll take that, what do we need? Surface area is 5 centimeters squared. 5 times 0.01 squared. The T infinity is equal to 23 in degrees Celsius. Then we've got our total is equal to our paste plus our Cu plus our conv. Our paste would be equal to the thickness of the paste, which is 50 microns, 50 E minus 6, divided by K, 150, times the area. The resistance of the copper is equal to the thickness of the copper, which is 1 millimeter, divided by K copper times the area, and we're going to need to figure out what the conductivity of copper is. Did they give us that? No. So we're going to have to go back to the textbook to figure that out. And the convection part is equal to 1 over h times the area. And the convection coefficient is 5,000. Okay, so we'll need to figure out what the conductivity of copper is. So jumping over to the textbook in section 16.2, we've got this handy table of thermal conductivities, and you see there that copper has a conductivity of 401 watts per meter squared Kelvin. So we can put that in. Conductivity of copper is 401, and there we go. So now we can evaluate what the total resistance is, and we get a total resistance of 0.4, which tells you that the final temperature, T GPU, will be equal to Q dot times R total plus T inf. Substituting in Q dot is 200. Then we've got our GPU temperature is 104 in this setup. So that sounds like it's running pretty hot, but I guess it's not totally ridiculous. Probably not so great for it. I've seen GPUs run that hot back in the early days of Bitcoin mining. Definitely kind of messed up some graphics cards through prolonged operation at that temperature. You can do some crazy stuff to them like that. So in the second part of this problem, we're going to need to deal with thermal paste instead, and or rather, we're going to get rid of the thermal paste. So instead of the thermal paste, we're just going to have the solid connecting to the other solid. And when you have solid connecting to other solid, we now need to account for a contact resistance. So the thermal contact resistance is to deal with the fact that you have imperfect contact from one surface to another one. So this is set up in the I believe end part, 17.2 is where the book has some awesome pictures of this. So if you have perfect connection from one solid to another, then in theory you would have this kind of a setup, but in reality there's some surface roughness, and to account for that, with this imperfect contact, we need to deal with contact resistance. If you have a thermal paste filling in the gaps, and that's not the case anymore, and you move closer over to this situation, but now having to account for the resistance of the paste. So when we have thermal contact resistance, this is quoted as really like 1 over HC. So it's not in exactly the correct units for us to be able to use it in the problem right away. You see these contact conductances defined as watts per meter squared Kelvin. That's the inverse of this thermal contact resistance. So what you do is you take RC and you divide it by A in order to make an actual resistance. So calling it thermal contact resistance is a bit of a misnomer, but yeah. So in part B, we have instead our total is equal to our contact plus our Cu plus the convection resistance on the other side of that, and our contact is equal to RC divided by area. So the reason for this is that it's 1 over HC area. It works like a convection coefficient, and RC has the units. You can see that would give you, after you divide it by area, kelvins per watt, which is what the thermal resistance is supposed to be equal to if we're going to be equating it to a temperature difference divided by a power. Okay, so that means in this new version of the problem, we're instead going to say that R total is equal to not the paste resistance, but RC, which is 3e minus 4 divided by the area plus that. And now we've ended up with a temperature that's much higher, so 224 degrees Celsius. That is less likely for the GPU to survive at, so that's definitely no good. And that's why you want to use thermal paste. Okay, question 2. Suppose you're sitting in an attic where a thermometer reads 22 degrees C. Explain why this feels much warmer in the summer than the winter. Okay, so if you're just sitting in a room that has normal kind of not intense airflow, then heat transfer is about 50% from natural convection and 50% from radiation. The natural convection is based on the temperature of the air relative to you, and the thermometer is really measuring the air temperature, whereas the radiation is based on the temperature of the walls relative to you. And if you're in an attic where the house is kind of in contact with the outside through not that thick of walls, and all the walls are in contact with the outside basically, like the ceiling walls, everything except the floor pretty much is going to be directly in contact with the outside if you're in an attic, then you've got a lot of surfaces in the outside of the room that are going to be much colder in the winter than they are in the summer. So in the summer, on a really hot day, where let's say the walls themselves might be close to 40 degrees C, similar to the temperature that you might be at, then the radiation might be heating you up. So the natural convection is cooling you down, but the radiation is heating you up a little bit, and you've got a lot less heat transfer, heat dissipation from you compared to in the winter when the walls might be very cold. So maybe the walls are only at like 3 degrees if it's a very cold day, or perhaps even below 0 maybe. Then the heat transfer from radiation is going to be much more if there's a bigger temperature difference between you and the walls. What does sitting in front of a fan do in each case? Well, sitting in front of a fan is in either case going to make you feel colder. Why is that? Because it enhances the convection to the point that the convection dominates over radiation, and you don't really have to worry about the radiation so much. Now that so since the radiation was cooling you down too much in the winter, perhaps that might sound like a good thing, but as long as the air is still colder than you, then that's going to enhance that heat transfer and still ultimately cool you down. So it makes convection, this causes forced convection, which is generally dominant over radiation and natural convection. So that means that we are going to be experiencing more cooling towards this 22 degrees C. For the following picture, assume K1 is the conductivity here is bigger than the conductivity here, which is bigger than the conductivity here. And sketch heat flow lines. So let's say temperature 1 to temperature infinity. It doesn't matter. They could be going to the right. They could be going to the left. It doesn't really matter for what the question's trying to get at. Heat flow lines under the isothermal normal surface assumption, and then under the adiabatic parallel surface assumption. Then approximate actual heat flow lines. So what this is getting at is, in this chapter, what we're dealing with is methods to add sections in parallel for thermal resistances in parallel and in series to deal with something like this. And the first thing you can do is you can say, all right, let's assume that that every normal surface, so if we're kind of conducting from left to right, then a normal surface would be something like this one, the junction of K3 with these other ones. So this is a normal surface. If you assume that that's an isothermal, then you imagine you're going through K1 as fast as you would go through K1, and then this whole surface over here is an isothermal, and then the whole surface over here is an isothermal too at the other side of K2. So you could have really dense heat flow lines that are completely horizontal here, and then there might be a difference in heat flow lines over here. So a different a different density at the top versus on this part. So why don't we grab some paint for this? Don't be alarmed by these statics in the background. And we'll get a new template here. Let's try that again. Copy this and paste it over here. Okay. So we'll draw some lines. Let's get, actually, why don't we preemptively go and grab a couple of different copies of this thing. Okay, perfect. So in the isothermal normal assumption, we'll get some heat flow lines. Heat is red, as everybody knows. That's sort of obvious. So we've got some, if K1 is really high, then we'd have very dense lines up there, and then K2 is low. So we've got sort of sparse lines over in this part. And then K3, under the isothermal assumption, we'd want like 5 evenly spaced lines, kind of just as many in the bottom area as the top. So essentially what we're saying is we've got fast heat conduction through this top part, and then slow heat conduction down here, and then it just evens out once you go over to this part, so it just jumps down immediately. That's the isothermal normal assumption. Under the adiabatic parallel assumption, instead what you say is, rather than imagining that you've got these, so this first situation, you'd essentially you'd use that to say we've got these two things in parallel, and then that equivalent thing is in series with this whole equivalent thing. That's the effect of using that assumption to add the resistances. Instead of that, you could say, all right, let's say that this is kind of like a split right there, and view K3 as two different parts. So this first one, you kind of make a big deal about that line and view this is in parallel, and then add that in series with this. And then in the second assumption, the adiabatic parallel one, what you do is you say that we're going to only conduct through the top here. So that means we've got maybe 3 is a bit too much, because it wouldn't be quite as much conduction as we had through this top part in this previous one, but the conduction is going all the way through. And then down here we would have certain conduction going through that as well, perhaps less if K2 is a lot lower. So the adiabatic parallel assumption, you'd take this in series with this part, and then this in series with that part, and then when you're done that, you would add both of those in parallel to figure out the total conduction. Now, in reality, what would happen is something that's kind of a compromise between each of these situations. So it's not true that all of the heat that goes through the top part has to can jump down and go anywhere in this part, and it's not true that all the heat that goes through the top part has to go through the top part on the other side too. So you'd expect something kind of like this at first, and then when you get towards the boundary, things can start to spread out a little bit more and equalize as you get over to this part. So this is going to be a little bit trickier to draw. Let's give it a shot. So we'll try something like that, and maybe kind of moving down a bit, and then same thing with that one. And down here, what could we do? That one might also be sort of moving down. There's not enough space there for it to spread out. Mostly moving down because these other ones over here are going to be moving down as you end up towards that. Yeah. Okay, so something like that perhaps, where it spreads out into this this section over here as we've moved across. Right. So essentially what this means is that although both of these assumptions are incorrect for what's actually going on, you'd expect that the real heat the real conduction is going to be a compromise between each of these situations. So to be somewhere between what you would get using this calculation and this calculation, where this calculation is going to underestimate the actual resistance, and this calculation is going to overestimate the actual resistance. And so the fact that although they're different, they are bounding the answer tells you how, gives you a pretty good idea about what the range of the real value is going to be.